Hello, it's Mr. Canfield. So today we're going to look at the graphical approach to limits. This is chapter 4 in our book, or section 4, whatever you want to call it. And so the idea of a limit, we talked about this the very first day of class, is, so if let's say we're looking at this picture here, and we want to find the limit as x approaches 2, which that says 2. Again, yeah, it's kind of visible in the camera, but so that's like, hey, if I put a pencil over this, what is the expectation? When x is equal to 2, like, what do you think it's going to be? And in class, we like open it up and like, aha, there's nothing there. It's a ghost, or it dips and does something weird. Remember, it doesn't matter what it is. What it matters is it looks like it's going to hit the y value 10. And so we would say that the limit as x approaches 2 is 10. And we're going to look at this in a couple of ways today. And the first way we can look at it is, that was the first way. The second way we can look at it is if I plug this into the calculator and use a table like we did before. So be careful. Plugging this in like this is kind of the natural way that a lot of us will go and plug things in because we understand what we mean. Right now, what you're doing is you're saying take x cubed and then subtract 8 divided by x and then subtract 2. Without putting parentheses on the top and bottom, you're doing it wrong. And sure enough, if you, I gotta zoom standard. If we look at the picture, it looks nothing like this. So I need to go back in. I've got a surprise for some of you. Above the delete button in blue, it says INS. If you push second and then delete, it changes the way the cursor looks, and I can insert things before the cursor. So like, I'll highlight where I want to put something before it. I'll push the second and delete, and I'll put it in. So that saves me having to retype the whole thing. And so, okay, it looks a little bit different, but his scale is different than mine. Something that you might notice is that, here, let me make this look a little bit more similar to his. He starts at 0, he goes to 20, and he's going by 5s. So something you're going to notice is at 2, you don't see the hole. But if you push the trace button and type 2, you'll see that the y value is not actually there. So, and that's because we can tell from the actual equation, x cubed minus 8, x cubed minus 8, x. X cubed minus 8 over x minus 2. If we plug in 2, that breaks it. We're dividing by 0. That's a domain problem. So if we go in to our table and we kind of follow this table, then we're going to say, okay, 2, I don't care about actually filling in 2 right now. So ignore that. But I'm going to go in and -1.75. So in this class, you're required to do 3 decimal places at least. So you may round to 3 decimal places, but any less, you lose points every time. I mean, unless it's a perfect number. So like if it's exactly 1.5, then you can write 1.5. Okay, so I got, and so highlight over here. So this one's exactly 11.41, so that's fine. And but this one I need to write, it might feel weird writing it, but 940, that 0 is showing us that this is accurate out to 3 decimal places. If we don't include that decimal place, then it doesn't show that it's accurate out to that. So we're going to leave this alone for now, because this is what we're going to call the limit. Oh, that's 12.61 right there. Okay. But what you're going to notice, potentially, you might not notice. Oh, excuse me, I'm boring myself. No, I'm just tired. Okay, what we're going to notice is that if we look at these y values, 3, 15, okay, that's 1.75 and that's 2.5. So that's like here and then here. But then, as we get closer, so at 1.9, that's like here, right? And then here, and then here. I have a very strong suspicion. Oh, it's not 10. Oh, it's going to be a little bit more than 10. Our limit is what it looks like these are approaching. We call this the left hand and the right hand. Left is the lower numbers, right is the higher numbers. The left and right hand are both approaching what looks like 12. And so our limit actually is 12. Now the actual f of x, f of 2, f of 2 is undefined, and we can write DNE for does not exist, or you can write undefined. But the notation that we use is down here. It says the limit as x approaches 2 of f of x is equal to 12. Or we could write limit as x approaches 2 of the, and then write the function and is equal to 12. And so it's saying the function, when we plug in 2 to the function, we don't get anything. We don't care about that. What we care about is that it looks like they're going to 12. So big distinction there. So let's look at this box. It says the limit of a function. So limit of f of x. Try again. The limit of f of x is x approaches some value of c. So c is an x value. This is some number. C is a number. As x approaches a number, from the left-hand side, we write it like that. So it's got the minus sign after it. This is like the only place you're going to see this in math. You're going to see a little minus sign after. You'll see a little plus sign after. Those are called the left and the right-hand limits. So like left-hand side coming in from this way, right-hand side coming in from this way. In order for a limit to exist at x equals c, the only way a limit exists, this limit exists, it was 12. The left and the right hand, they're both going to the same number. If they're going to a different number, the limit does not exist. So like, let's look at this one. Our left hand limit. I think I said ham. Our left hand limit as x approaches 1. It looks like it's approaching the y value of 1. What about the right hand limit? From the right-hand side, it's approaching 2. That means that the limit as x approaches 1, those aren't the same thing. The limit does not exist. Hey, what's f of 1? That means what's the y value when x is 1? Well, we go in here and we go, oh, okay, well, the y value is wherever it's filled in, right? So the y value is 2. Now on this one, let's find the limit as x approaches 1. Again, okay, so looks like it's going to -1. What about this one? One from the right-hand side. All right, so it's going up to 1. Oh, I can't with the sound effects. It's not on purpose. So the limit as x approaches 1 is, we don't like split the difference. We just go, oh, since they're not the same limit, does not exist. However, what's the dot at x equals 1? It's 1. Okay. So let's keep going. Now we've got these guys. Okay, we have a little bit of a problem. It looks like they messed up their layers on their picture. This should be an open circle without anything there. It should be an open circle without anything there. Like it shouldn't be going through. So this one, the limit as x goes to 1 from the left, we wind up getting 1. From the right-hand side, we get 1. So that means that the limit as x approaches 1 is that y value, 1, since they both were going to the same y value. How about this one? It's the same picture, right? Except it's got this dot down here. So still, as we approach from the left, we go up to 1. We're also going up to 1 this way, meaning our limit is 1. But this time, oh, I skipped this last one. Okay. This time, it's filled in down here, that means that f of 1 is negative 2. What about this one? There's no dot. That means f of 1 does not exist, or it's undefined. Oh, by the way, this shorthand DNE, 100% acceptable on the AP exam, 100% acceptable in my class. I will always know what you mean when you write DNE. It doesn't mean like do not eat or anything like that. This is known language, known jargon. Those were both wrong. It's a known abbreviation or acronym. Let's see. When there's a vertical asymptote at x equals c, that means the limit doesn't exist. So in case you don't know what we're talking about here, like on the two ends of this, the way that it's stopping, it's doing something like this. So if the function is going up, approaching the vertical asymptote, we say that the limit as x goes to c is infinity. But this one, since it's going down, okay, this block of text has a couple of issues. We'll talk about it. Okay. So, this block of text is not referring to this picture. I mean, I totally did this before the video, and I'm just doing it again. And since we're finding the limit as x approaches 0 in this one. That's like, bam, the x value of 0. Okay. From the left-hand side, we're like whoosh, going up to 1. From the right-hand side, we're whoosh, going up to 1. That means that, like, the limit's going to 1. Hey, what's f of 0? It's also 1. So a lot of times, the limit and the function are the same thing. We've been focusing on special scenarios where it doesn't happen, because those are the weird ones, and those are the ones that are worth talking about. And it's like, well, yeah, of course, it looks like it's going there, and it is there. That's pretty normal. All right, moving on. So now we're talking about asymptotes. Okay. The limit as x approaches 2, but from the left-hand side. So 2's right here, and we're going, whee. Does this ever touch the dotted line? No. So because of that, they're getting closer and closer and closer, but never touching. This is going down, 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 down. That means it's going to negative infinity. This one, whoop, it's going up to positive infinity. Are those the same limit? No, that means the limit does not exist. And there's an asymptote there. F of 2 also does not exist. All right, so now we've got this one. It's a bottomless pit. So as x approaches negative 2 from the left-hand side, it's going negative infinity. From the right-hand side, negative infinity. So what's the limit then? We can say the limit as x approaches negative 2, they're both going to negative infinity. We can say it's negative infinity. Some people don't write negative infinity. Some people will just write does not exist. You'll lose points for that in my class. You need to tell me that it's going to negative infinity. So I know I'm the worst. It's okay though. So the weird thing is both sides are going to negative infinity. But if you notice, when x is actually equal to negative 2, there's a dot here. And so that means that f of negative 2 is actually the y value of that dot, which is just 0. So a little kooky, but that's okay. All right, let's see what's next. All right, so I'm not going to read his text. You certainly can read his text. I'm just going to answer his questions. So this one says, what's the limit as limit as x approaches negative infinity? That means what if we go this way forever? What's the graph doing? What's the y value going to? And so the y value just keeps going up forever and ever and ever. That means it's never going to stop going up. That means we're going to say our limit for that is infinity. And similarly, if we go off to the right-hand side forever and ever, we see it's going up, 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 up. This is like end behavior, if you remember that from pre-calc. That limit is also infinity. So this time, when we go off to negative infinity, it's going zoop, it's going up, so it's going to positive infinity. And then when x goes to regular infinity, when x is going this way, it's going down. So we can say x is going to negative infinity. Notice that when we have positive infinities, we don't need to write the plus sign in front of it. We just leave it. Just like, if I have positive $5, I don't write positive 5. I just write 5. All right. More asymptotes. All right. So this one, the limit as x approaches negative infinity. So this one, there's a horizontal asymptote. It's getting closer and closer and closer to that asymptote. Oh, so it's going to 4. And as we're going out here to positive infinity, it's getting closer and closer to that guy. So it's going to negative 2. Just the y value of the asymptote. All right. Someone drew squiggles on my picture. This one we're going off to negative infinity. So I want to make sure, yeah, okay. We're going to contrast these two in just a moment. Contrast means look at the differences. So this guy goes and then gets smaller and smaller and smaller. If you've studied springs, this is like a dampened spring or damped spring, something like that. It has dampening. So it gets closer and closer and closer to our asymptote as we go out to the left. And so as we go out to negative infinity, it is going to get closer and closer and closer. The squiggles are going to get smaller and smaller and smaller. So we'll say that our limit's 1. And off to the right, we'll say, same deal, it's getting smaller and smaller. So we'd say our limit is that y value of 0. But this one, as we go off to negative infinity, it is bouncing down and up and down and up and down and up. We call this oscillating. That's O-S-C-I-L-L-A-T-I-N. That's oscillating behavior. Since it's oscillating like that, that just means bouncing back and forth between the same two things. It's never getting any lower. Does it end at the top? Does it end at the bottom? Does it end in the middle? And end is not really the right word. Infinity doesn't end. But since it's constantly bouncing, we don't take an average, we don't do anything like that. We just say that limit does not exist because it's oscillating like that. Now this one, even though the squiggles are getting smaller, the squiggles are going up. So it's going to be like, whoop, and it's just going to keep on going up and up and up and up and up and up. So since it keeps on going up and up and up and up and up, we could say the limit is infinity. And that, ladies and gentlemen, is how we think about limits graphically. Hope this video was helpful. Like, subscribe, join my Patreon. No, just kidding. I don't care if you do any of those things. I don't have a Patreon. I'm not getting one because I do these for free. I really hope that that I can be helpful. And if you do watch these videos and you're finding any use of them, but you're like, you know what, I really wish he would do this. This would be more helpful. It doesn't matter what it is. Tell me what it is. I'll do it. Or I'll try it. Or I'll consider it. If you're like, Mr. Canfield, you should dance around in circles and film yourself doing it. I'm not going to do that, but hopefully you understand what I mean. Have a great day, everybody. Bye-bye.